Alright, so in this video, I'm going to show you how to memoize a function in JavaScript. And after I implement that, I'm going to show you two examples. And I really want you to wait and see the second example because that is going to show you the beauty of the memoization function that I'm going to create. So first of all, what is memoization? Well, memoization will basically allow you to cache your function calls. Meaning that let's say if you have a function that has some expensive call, let's say it takes some time to compute, then what happens is, let's say you need to call that function multiple times, and because that function is pretty expensive, if you call that function multiple times and it computes its logic multiple times, which is a heavy calculation, then there's a chance your application can become slow because it always has to compute that heavy calculation. But what memoization allows you to do is, once your function has computed all the heavy logic, the memoization function will help you cache that result so that the next time that function is invoked, if the arguments passed into the function is the same as the previous function call, then the memoization function is going to make sure that the function doesn't recalculate itself from scratch, and rather it just picks the result from the cache and displays it. So this allows the code to skip out on that complete heavy calculation, provided that that function was called before and its result was stored or cached somewhere. So the subsequent or the next time we call that function, we will always pick the result from the cache. So that is what memoization will help us do. It will simply help us cache our function calls to prevent expensive calculations. Alright, so just remember that for now you will understand things very clearly as we implement this. So first I'm going to show you with an easy example, and then in the second example I'm going to add a little bit of complexity to show you the beauty of that function. Alright, so first let's say I'll create a function, any function, let's name it expensive function. Alright, and let's say this will be an arrow function, and all this is going to do is to just make this an expensive call. I'll just create a for loop. Let's say let I equals 0, I less than, and let's add a very huge number, something like that, and then I plus plus. Alright, and then in the end we simply return just any random number, let's say 5. Alright, so once this entire loop has been completed, only then we go over here. Alright, let's say here we just simply write continue or something like that, doesn't matter. So this is an expensive function, right? Now every time I call this function, this entire loop is going to run, and then whatever it needs to return gets returned. That's not a good practice, right? That every time I'm calling this function, this entire calculation has to be performed before we can return the same value. So wouldn't it be nice to have a way where, let's say if the inputs or if the parameters were same, which in this case is nothing, then for those cases, wouldn't it be a good option where, let's say if the argument passed to expensive function was always same, then the second time the same function is invoked with the same argument, we make sure that this calculation doesn't happen again, because we already computed that the last time. So why compute it again? Why not store that value for that argument somewhere and then just extract it from there? So let's say I just pass in an argument over here, let's say something like 3, and this will be n, alright? And let's say over here, instead of continue, I do something like, let's say I create a variable over here, sum. So over here, let's say I can write something like sum equals n plus I. Alright, and instead of 5, let's just return sum over here. So now this calculation depends on the input over here, right? So for the same input 3, this logic is always going to return the same result, right? Because it's calculating based on this n, which is 3. So when we call this once and we get a sum returned, and then let's say we want to call it again with the same input, then we should not want to go through this computation again, because that's going to become so much heavier and so much expensive. So we should have a way to memoize this return sum the first time this function was called with this particular argument. Alright, in that case, the next time we call this again, we don't have to compute this all over again. So how do we memoize this? Well, it's pretty obvious, right? We need some sort of a variable, or let's say an array or object, where we can store the result of this particular input. Alright, so the base logic is that simple. So the basic idea is that simple, that whatever this input returns, we need to store this input as a key and its respective value, which is the sum, as a value of that key. So what does this bring in your mind? Objects, right? Because objects can store key value pairs. So this means we can store the result as a key value pair format in an object, and then the next time this is called, we can simply retrieve that key from the object by checking if that key already exists. If it does, then just return me the result or the value of that key, and in that case we don't have to iterate through this again. So let's build that logic. Alright, so what I'm gonna do is I'm gonna go right up here, and I'm going to create another function named memoize. Alright, this will also be an arrow function, something like that. And what I'm gonna do is I'm gonna copy this memoize, and I'm gonna actually wrap the memoize around this expensive function. Alright, so just like that. And for now, let's not invoke it anymore. Alright, so this means I'm wrapping something around the expensive function, which is nothing but the memoize function over here. So since this is receiving a function, we can pass fn over here. Alright, fn is going to refer to this function, and this memoize function ultimately is going to return another function. So it's basically going to do something like this. We're going to have return, alright, and we are going to return a function. So it's going to return another function which is going to get stored in the variable we assign this memoization function call to. Alright, so I can write something like const sum of expensive function, and I can equate it to this. Alright, so this much is pretty self-explanatory. Memoize is a function which takes the expensive function, or the function that we want to memoize, as an argument, and then since memoize is a function and we are calling this function, so then if you're invoking something like this, then it's going to invoke this function over here, and we know this function over here is going to return another function that's going to utilize the fn, or basically the expensive function, to basically create a cache and return us the value if it exists in the cache, or just simply call the expensive function if it does not include in the cache, and then add it in the cache once it's done with the calculation. Alright, so for now we are just calling memoize function, which takes the expensive function as the argument, which is the fn over here, and whatever this memoize returns, it's going to be stored in the sum of expensive function variable. Alright, that's pretty simple. Now let's memoize the result of this. So to memoize the result, as I said, we need an object, right? The object where we can store the key value pair. The key will be the input that we pass, which was 3 in our case, for the n over here, basically when we were doing something like this. Alright, I'm just going to comment this out. So 3 is going to be the key, and the value is going to be nothing but the sum, the final sum. So in the memoize function over here, what I can do is, first, I can create a variable named const cache. This will be an empty object, and this object is going to be utilized over here in this function. Alright, and you know, if this function is within this function over here, then this function forms a closure with its top level, which is this function. Alright, and because this function forms a closure with this area, so this function can always access the cache. So this is nothing but a global variable for this function. Alright, now the benefit of doing this is, because memoize returns a function as well, so later on we are going to invoke sum of expensive function, and we are going to pass the value 3 over here. Alright, now the benefit of creating this closure is, no matter how many times I invoke this, alright, for each of these function calls, the cache is going to maintain its latest value. So for example, let's say I pass 3 over here, 2 over here, 1 over here, then for each of these values, the cache is always going to maintain the latest value. So for example, for 3, whatever this returns, that's going to be added in the cache. Then when this one is called with the input of 2, then when it checks the cache will be having the key value pair of 3 during this invocation. And similarly, when this is invoked, the cache will be having the properties or results of 3 and 2 in its object, or stored within it. So for each of these function calls, the cache over here is going to act like a global variable that keeps track of the key value pair of the respective function calls, and it's always going to maintain it throughout each and every function call. Alright, so let's just remove these two for now. Let's also remove this for now to just avoid the confusion, because you might be confused, right? Why are we passing 3 here? How is that going to add up in the end? Well, you'll see that, don't worry. So actually, instead of removing that, let me keep this, because this is going to help you understand things better. So in the end, instead of calling expensive function of 3, we are going to call sum of expensive function of 3, right? And we know this sum of expensive function is going to be nothing but this part over here, because it's going to include whatever memoize returns, which is this. So when we call sum of expensive function of 3, which is this part, alright, then this is going to be invoked. So this over here is receiving that 3 input, which means this is going to receive an argument. So we can write args, and instead of just writing args, we can actually spread it out. Because let's say we were passing multiple inputs over here, which in our use case right now won't make sense because we are only taking one input over here. But let's say for some different example, we had multiple inputs, then passing it like this would be a good option, because it would just spread out all the inputs over here. Alright, but in this case, since we are only passing one input, this ... args is going to be nothing but n, which is going to be nothing but 3. But for good practice, let's just spread out the args like this, because it's going to help you understand things better when I show you the second example. Alright, so now we have 3 getting passed over here, right? So as I said, whenever we call this, alright, we will go over here And the first thing we need to do is we need to check if the result of 3 after this calculation is included in this cache. If it is, then simply return that value. Basically return that value from the cache. And if it's not, then invoke this function over here, which we can do from fn over here, inside here, perform that calculation, and then store the key, which is going to be 3, and the sum, which is going to be the value, the entire key value pair, in the cache object. So pay attention. What I'm going to do first is I can write const, let's say args args to string equals json.stringify, and I'm going to stringify nothing but the args. Alright, so just know that args being spread out is going to include 3, but just args, if we just console log args, that is going to return us nothing but an array. Alright, because that is why we are able to spread this out, right? Because it's an array. And if you pass anything like this in the function parameter, then this part over here acts as an array, but if you spread it out, then it gets spread out as individual elements. So when we do json.stringify args, this will return nothing but something like this. It will return a string, and it will have an array which will include nothing but 3. Alright, to show you that, let me do console.log and then args to string. Alright, I'll open my inspector, then the console. Alright, let me just refresh this. So here you can see 3 over here, and this 3, to show you, if I write type of, you can see it's a string. Alright, so basically it gets stored like this in the object. Alright, so basically we get this entire string with the array of 3. Alright, so why are we doing this? Well, because we want to take this part and we want to store this in the cache object. Alright, so for this particular input for 3, if we convert this to a string and we store it over here, alright, so we are converting this to a string because to store it in the cache, which is an object, we will have to convert this to a string. That's basic JavaScript. So to show you what I mean, I'll write here if args to string in cache. So if args to string, which is 3, let's say, for our example, if that already exists in cache, then you can just directly return it. So return cache args to string, right? So from the cache, it's going to search the args to string, which is this part. And we know in JavaScript, to access a particular key in this format, this part has to be a string. Alright, that's why we converted this input to a string like this. Alright, so if it already exists in the cache, then simply return the result of that. And if it doesn't exist, then what we can do is else. Over here, I can write const result equals, you guessed it right, I can simply call the fn, which is nothing but the expensive function. So if it doesn't exist in the cache, call this expensive function, compute the result, get the result from here, which is going to be the sum, that will be stored in the result. So we'll just call fn, and you guessed it right, we will simply spread this out over here, which as you know was 3. So 3 is going to get added over here. So expensive function is going to get called with 3 as its argument. Alright, then this is going to get computed, then the sum is going to be returned, which is going to be stored in result. And once we get that, what we can do is we can then store that result in the cache. So cache of args to string, so cache of 3, this one over here, is going to be nothing but result. So now for that particular input, of 3, we did store it in the cache. Alright, so the key is going to be this, and the result is going to be whatever the sum is returned from here. And then we can simply return nothing but the result. Alright, so whenever this is called, we are going to go over here. Alright, then it's going to check in the cache if for the input of 3, basically it's first going to convert this to a string, then it's going to check that does this key over here for the input of 3 exist in the cache. If it does, then directly return its value. If it doesn't, then call that function that we had passed from over here in the memoize. Alright, and because of closure, we are able to access that fn from here. Alright, so call that function if it doesn't exist in the cache, pass in 3 over here, let the computation happen. Whatever the result from that computation is returned, store it in our result variable, then store it in the cache so that the next time we invoke this again, we can directly retrieve it from the cache and then return the entire result. So when this function is called, at last we will get the returned result. Alright, and this result is nothing but this result, which is nothing but this returned sum. Alright, pretty simple. So now to just see if we get the value, I can write console.log and I'll put the other bracket over here and I'll save it, and there you go. You see, we get the value, so everything works perfectly fine. And if I called this over here, then in this case also we would get the same value, just to show you that. I write console log and console log over here, you can see we get the same values. Alright, so this means our memoize function works perfectly fine because it returns us the right result. Alright, so now what's the benefit of this? Well, to show you that, let me first comment this out. Now what I can do is, to show you the benefit of calling the memoized function, I can actually show you the time difference between the function calls. And to make things more understandable or more readable, what I can do is I can actually rename this to something like memoized sum function. Alright, or let's say memoized expensive function. Alright, and let's copy and paste this here. Now I'll show you the time difference. So what I can do is I can first write console.time. Alright, and then I'll actually copy this. I'll actually paste this 2 more times over here, and this will be nothing but a string. Don't worry, you'll quickly see what I'm doing. Let me just clear this console, and then this part is going to be nothing but console log, and this is going to be time end, and this over here is also going to be a string. So this part over here is going to print us the time it takes for this function call. Now before I do anything else, let's first check that. If I save this, you can see it takes this much time. Alright, so it returns this output, and the first time it's called, it takes this much time. So 136 milliseconds, that's a lot. Alright, now let's say I copy this, paste this here, and let's actually name this first call to make things simple, to keep things simple. Let's remove this from here, and let's copy this here as well. Let me just remove this for once. Alright, so for the first call, it takes 140 milliseconds. Now I'll copy this, paste this here. Let's name this second call. Alright, now you'll see the difference. Alright, so after the first call has happened, the cache should now have the value for 3. Alright, the key value pair for 3. So the next time I invoke this, it should directly retrieve it from the cache. It should not go here, call the function, perform this expensive call and all that. So let's see if that works. If I save, and voila, you can see for the second time, the time taken is only 0.04 milliseconds, but the first call is 142.53 milliseconds. That's such a huge difference. Isn't that amazing? So this is the power of memoization. Alright, let me just remove this from here as well. So that's pretty cool, right? You can see the amazing performance optimization over here. Alright, so this works fine, right? But now let's just take this one step further. So now I'm going to show you another example, and you're going to see the beauty of this memoize function. So in this other example, I'll keep this logic as it is. We are not going to touch this, but I'm going to give you another example of the function that we're going to memoize, which in this case is going to be a factorial function. Alright, you're going to see the benefit of this memoize function in recursion. Alright, so what I'll do is, let's say I'll just comment this out. Then over here, instead of this expensive function, over here itself, let's say I'll create the factorial function. So I'll just pass this callback, right, which will be an arrow function. Remember, I can either create a factorial function outside just like I did over here, or I can create it inside as well. It doesn't matter. It's a function at the end of the day. It's a function that's being passed as a callback to the memoize function that we have created over here. So it doesn't matter. I'll just create it over here, and this will take an argument, let's say x, and let's actually name this factorial. And for now, we'll just comment this part out. Alright, so factorial, and then let's just quickly write the logic of factorial over here. So for example, if you need to do factorial of 3, then factorial of 3 is nothing but 3 into 2 into 1 and so on, which is nothing but 6. So it goes 3 into 2 into 1 and so on, right? So we can just simply write return x into factorial of x minus 1. Right, and for the base case, because we have to stop the recursive call somewhere, right? This is nothing but a loop. Consider this as a loop, but we need to stop it somewhere, otherwise it runs endlessly. After it goes to 0, it will go -1, -2 and so on. But we know in factorial that the factorial of 0 is always 1. So we can simply write if x equals to 0, then simply return 1. Alright, so this is the factorial logic. And if you had wanted, you could have copied this, pasted this outside of here, named this factorial, or just any name and passed it inside over here. Alright, that doesn't matter, it's your choice. Alright, so now to invoke this, let's just copy this, paste it over here, and let's say I'll write factorial of 5. Alright, and I'll need to console log this, but before I do this, before I call this like this, I want to do something else. Let's say instead of passing this as an arrow function, what I'll do is I'll convert this into a normal function. So I'll remove this arrow, and I'll call this fact, so nothing but function fact, and I'll call fact over here. This is the same thing, right? We're calling the fact function again and again, and that's going to go on to the recursion and so on. And the whole thing is wrapped in the memoize, which is over here. All right, so now you'll see the difference. All right, so let's say I call this console.log factorial of 5. And if I save, there you go, we get the answer 120. So this works fine, right? But now I want to show you something. There is a difference between calling factorial like this by creating a function here and writing it the other way around where I had added the arrow function. So hang on. What I'll do is over here, every time we store the result in the cache, what I'm going to do is I'm going to write console log and I'm going to print the cache result. All right, so cache. Now notice here, when I call 5, the result of 5 gets cached over here. All right, and then we get 120 as the final result. Now let's say I am calling nothing but factorial of 6. All right, when I call factorial of 6, so when factorial of 6 goes through its calculation, because we know this cache is a global variable for this over here, so when factorial of 6 is called, the result of factorial of 5 is already there. All right, the result of factorial of 5 is already there. But because we are invoking it in this manner, we are never really getting the chance to access the 5 over here. All right, just think about this once. So if function factorial is defined like this and we're calling factorial from factorial over here, then let's say, you know, right, the memoize takes the function as the callback, it's being passed here, and when we call this over here, factorial of 6, it's basically going to call this function, and the args is going to be 6 because this is the argument. So 6 is going to go inside this. It's going to see, does the cache contain the input 6? It doesn't, so it will call the fn over here, and the fn is nothing but this part, right? This factorial function. So the moment it calls fn, it's going to go in here, and then fn of 6 will be called, right? Fn of 6, when it's called, it will obviously check if is 6 equal to 0, which it's not, so it's going to go here, and then it's going to call 6 into factorial of 6 minus 1, which is 5, and then factorial of 6 minus 1, which is 5. So factorial of 5 is going to be called, and 5 is going to be passed here again, which is again going to come over here, and then it's again going to call 5 into factorial of 5 minus 1, which is factorial of 4, and then it's going to go back here again. So it's going to keep recursively looping as we expected, but it's going to keep recursively looping in here. All right, so first time when this is called, it's going to invoke this with the value of 6, right? Because we passed 6 over here, but then it goes in here, and then the recursion happens inside this. It keeps happening inside this. All right, so when we do 6 into factorial of 6 minus 1, which is 5, so factorial of 5, this is invoking this part again, which is fine. But why do we need to invoke this part again when the result of factorial of 5 is already there in the cache, right? Why should we invoke this part again? So when we create a function like this and we call factorial of x minus 1 on and on again, it keeps on looping through within this, and then finally it returns the result that it does, but it only stores in the cache the result of the input, which is 6. And as we noticed, when 6 into factorial of 6 minus 1, which is factorial of 5, was called, it did not retrieve it from the cache. It instead called this again. Alright, but if it had directly retrieved the result of 5 from the cache, then it would have only had to do one computation, which would have been 6 into factorial of 5, which it could have retrieved from here. So do you understand the problem with calling it like this? The problem is that it does not retrieve the value from here. Sure, it stores the factorial of 6 in the cache. So when I call factorial of 6 again the next time, let's say I call this over here again, so this part is going to be memoized for sure. This part is going to get retrieved right away from the cache. But for a new number, factorial of 6, even if we were invoking it the first time, it could have at least utilized the input of 5 while computing its calculation. So in that way, its own first computation could have also become so much quicker. Right, do you get what I'm saying? So to show you something, let's say I copy this part, I paste this over here, then I uncomment this, and let's say I take the console log factorial of 6 and pass it over here. Alright, and then let's say I copy this again, and I pass it here. And this is going to be nothing but second call. So now here, if I save, you can see that compared to the first call, the second call was pretty less. Right, so the memoization works. So when we call factorial of 6 again, it directly retrieves it from the cache. But when this was called, alright, the first function call, this one, this could have also been way quicker if it could have directly taken the factorial of 6 minus 1, which is factorial of 5, from this cache. So this computation could have also been way quicker. We know that this one was quick for the second call because it was already memoized, but the first computation where it calls this logic and goes through each of the call recursively, this could have been quicker as well if it could have just directly retrieved the value of 5 from here. It would have had to go only one level down in that case, right? So if instead of writing function like this, we write the arrow function. So let's say I write this arrow like this. Sorry, my bad. And just put an arrow over here. All right, and we remove fact from here and we paste factorial here instead. Then now if I save this, you will notice something. All right, I saved it and you can see something special over here. Let's say I just clear the console, and for now let's say I just comment this part over here, and I'll just save it again so we can get the function call. So now you notice something. Now something very special is happening. All right, when I invoke it like this, rather than creating a function here with the name factorial and calling that function factorial over here, if we just put an arrow function and we invoke this, then what's going to happen is for every recursive call, so let's say if I pass 5, for every recursive call of 5, so 5, 4, 3, 2, 1, for each of those calls, it's going to save each of those values in the cache. So you can see before the result of 120 is returned, it's storing each of the value of 0, 1, 2, 3, 4, and 5 in the cache. Now this is something very special compared to the previous one. In the previous approach, where we passed the function directly with the function keyboard, it only stored the result of 5 in the cache. It only stored the result of 5. But in this approach, we are storing all the results, so 0 to 5, which gives us a new advantage, which is when we call factorial of 6 or 7 or 8 or anything, it does not have to compute the factorial of 0 to 5 anymore. So when we call factorial of 6, it won't have to compute the factorial of 0 to 5. It just has to go one level down, which is what makes this so special. In the previous case, when we called 6, it was going through the entire nesting process all over again, right? But in this case, it's directly going to retrieve 5 from here. And the specialty is, let's say we call factorial 5 over here, but then later on we call factorial of 3. It doesn't even have to do a computation then, because it's directly going to retrieve it from here. Same for factorial 0, for 1, for 2, or anything. Alright, so it makes the cache so much more proficient. So now just to show you what happens here, let's say I uncomment this out and I save it. So over here, you can see a few things. Alright, so when this is called, you can see the time has effectively reduced for both of these calls. Because even when this is being executed the first time, like this part, when it goes to our memoize function and it tries to see, like let's say 6 minus 1, 5. So then it's going to say, is the value of 6 minus 1, or is the input of 6 minus 1, which is 5, present in the cache? Yes, it's present. So give me that value right away, which it returns. And then it can just directly return the result from there. And then for the second call, it doesn't even have to go any level deep because the result is already there. So it just returns the result right away. All right. And now you might wonder, why is it that when I call factorial like this with an arrow function over here, that we get all the results passed down over here for each of the traversals? Instead of when I called a function with a function keyword, then only the key value pair of the final result was being stored. And why not each of the computations? Well, that's because you notice we are not calling the arrow function here for every factorial call anymore. We are calling the factorial over here. And we know the factorial over here is equal to nothing but whatever memoize returns, which is nothing but this part over here. So for each computation, let's say the first time factorial of 5 was called, let's say I just comment all of this out. So whenever factorial 5 was called the first time, what happens is it goes over here, checks in the cache. Of course, it's not present at that time because it's the first time we're calling it. Then it goes to the else, where it invokes the fn, which is nothing but this arrow function here. So when factorial of 5 goes here, calls this, and this gets invoked. So when we reach this line and it becomes 5 into factorial of 5 minus 1, which is 4. So here 5 into factorial of 5 minus 1, which is factorial of 4, calls this part again and not this part. Alright, so it doesn't get stuck in this loop here. It goes up here and it calls from here. So basically for factorial of 4 as well, it's again going to check, is it there in the cache? It's not. It's going to come here and it's going to call fn again, which is going to call this again. Then it's going to be 4 into factorial of 3. And then it's going to again go here and again call this, then factorial of 2. Then it's going to keep boiling down like that until it reaches 0 and it returns 1, which means for the input of x, when 1 gets returned, we are going to, while we come back from the recursion, like when we go 5, 4, 3, 2, 1, 0, then you know each of those function calls keep getting added to the stack. So when from 0, when we return 1, as we keep returning from each of those function calls in the stack, we keep adding the key value pair in the cache. So the result of each of the keys keep getting added to the cache as we iterate back from the recursive calls. So that's what allows each of these values to get added in the cache. So basically it's nothing but something like this. So say if I have this, and then let's say if the factorial was 5, then 5 first gets added. So the factorial of 5 is called. So it goes right up over here, then it goes here, it checks in the cache, it's not there. So factorial, so fn gets called again with nothing but the value 5 itself, which adds it to the stack over here. And then since 5 is passed down from up there, it comes here, then 5 into factorial of 5 minus 1, which is 4. So then 4 gets added over here. Alright, then similarly again, factorial of 4 is called, so it goes here. So fn of 4, which calls this again, then 4 into factorial of 4 minus 1, which becomes nothing but 3. So this over here becomes 3. Then similarly, that process basically keeps repeating for 2, then 1, then 0 over here. Then as soon as it reaches 0, you get 1 returned. So what happens when 1 is returned? So that means if we go up here, when 1 is returned, from here, it gets stored in the result, which then gets added to the cache, and then we return that result, which is nothing but we return 1 itself. Alright, basically because 1 was stored over here, right? So we store it in the cache, and then we return the result. So for 0, 1 gets returned from here, and then here 1 gets returned in the end, right? So we can write something like 1 is returned from here, right? 1, and then we know that when 1 was returned, we go to the previous function in the stack, which was nothing but x equals 1. So this was nothing but 1 into factorial of 1 minus 1, 0, right? And we know factorial of 0 has already returned as 1, so it becomes nothing but 1 into factorial of 0, which has already returned us 1. So 1 into 1 also ends up returning us 1, which was invoked from here. So this result also ends up getting 1. Then that's also stored in the cache, and then that 1 is also returned. So this means 1 gets returned from here as well. And similarly, that process keeps on happening, where in the next case, for 2, when x is 2, it's nothing but 2 into factorial of 2 minus 1, 1. So factorial of 1, we know factorial of 1 also returns 1. So then finally we end up returning 2 into 1, which is 2, which goes to the result over here, again stores it in the cache, and then returns nothing but 2. So this ends up returning nothing but 2. Then similarly, back again, this time we come to the 3 call stack where the input was 3. So 3 into factorial of 3 minus 1, which is factorial of 2, and we know factorial of 2 returned us 2. So 3 into 2 is nothing but 6, and then 6 is stored in the result. That gets added to the cache, and that is also returned. So 3 ends up returning us nothing but 6. Then we go to the previous remaining call stack, which had the input of 4, then 4 into factorial of 4 minus 1, so factorial of 3, and we know factorial of 3 returns us 6. 4 into 6, nothing but 24, and then we go up here again, 24 is returned from this function, 24 gets added to the cache for the key of 4, and then that's also returned. So 24 gets returned from over here, right? This is 24. Then after that, we go to the input of 5. So 5 into factorial of 5 minus 1, which is 4. And we know factorial of 4 returned us 24. So 24 into 5, which as you guessed is nothing but 120. So we go up here, fn returns 120, which is in the result, which gets added to the cache for the key of 5. And then 120 is returned finally. So this part in the end ends up returning nothing but 120, and that ends our entire stack. So basically, as we kept going back, we can say that these kept getting popped off, and then lastly after 5 returned 120, this also got popped off. Alright, and that's how, because we are calling this time instead of just iterating right within this when we had the function keyword call over here, this time because we are calling this, and for each recursion back up, we keep calling this function over here. So while we come down, it gets returned from here, and it adds each of the values for each of these input in the cache as we come back down. You understand? That's the benefit of calling it like this with an arrow function and invoking this part over here. That while it comes back, it's going to add each of the values for each of those keys in the cache while returning. And that's going to ensure that this entire cache stores the value of 0 to 5, basically all the values. So now if I was to call factorial of 3 or factorial of 2 or anything, in fact any number less than this, if I want to calculate the factorial of that, it will just directly retrieve it from the cache. It doesn't even have to calculate. And for factorial of 6, it will just go one level down and check that it does factorial of 5 exists. Then it's going to do 6 into factorial of 5, which is 120. So 6 into 120, and then that's going to return the result for factorial of 6. Alright, previously when we had the function keyword over here, when we call factorial of 6, it did not check the cache for the factorial of 5. It instead made the entire calculation and only added the factorial of 6 answer in the cache at the end of its recursion. But in this case, in this way, we don't have to trickle down on and on again. Alright, so that was the beauty of this memoize function over here. So when you use it with recursion, you can always call it in this manner instead of creating this with a function keyword and then calling it. But that also depends on your use case, because this can be very memory consuming because the object keeps getting filled. Basically the cache object gets pretty heavy over here if you store each and every result. So depending on the use case, you can decide to either call it like this or basically add the function keyword and then call it over here, which in that case it will just store the final result, which will make sure that if you call that final result again, so in that function keyword approach, if you call factorial 5 again, then it would return the answer right away. But if you call factorial 6, it would go through the entire process. Alright, so you can decide based on your use case if you want to keep the cache too heavy or too light. That's up to you. But these are basically two different ways to utilize this memoize function and manipulate the cache over here. Alright, so I think that was a pretty in-depth overview or a deep dive into how the memoize works in JavaScript. I hope after learning these approaches, you don't forget how this works and you get a better idea of how things work on a ground level, and not just in a way where we just code things out and then you have to manually go through things one by one and have a hard time understanding it. Alright, so you see how for different use cases, one for the expensive function call or for the recursion, you saw how for different use cases, how our memoization function can benefit us profoundly. So with that, that's all for the video. If you found it insightful, drop a like and subscribe for more.